the Ihara action on the gram fundamental group of P1 minus 3 points. First of all, I'll do a recap of everything I did last week for P1 minus 3 points. Then I want to go back a step and do the same thing for P1 minus 2 points, because I'm going to need it. And then in the second half, I'm going to study the automorphisms of this thing. And so this is where it starts to get a little bit confusing. So I'm going to write this up on the board as a sort of plan for the next 2 lectures. So what's going to happen is that we have some group that's going to act on some object x. Okay, x will be the fundamental group of P1 minus 3 points in some guise. G will be a motivic Galois group. That will be this afternoon. It will act through the automorphisms of x. So we need to look at the automorphisms of x acting on x. Nothing more complicated than that. Some object with its group of automorphisms acting on it. And this is what I'm going to study to death today. In this lecture, I'm going to describe the action of the automorphisms of the pi 1 of P1 minus 3 points on itself. And I'm going to give about 4 different equivalent formulations of this thing. So the confusing thing is that when x is, in some sense, a torsor over its automorphism group, what we find is that the automorphism of group is actually going to be isomorphic to x. Not as a group, of course, but just as spaces in our case. And so what this will give is, in fact, some kind of multiplication law from x cross x to x. So this is where it starts getting confusing, because it looks as if x and x are playing the same role here, but they're not. And in the literature, this has been a bit of a... Can this give you a psychological block, this thing? So.
Confusion comes probably because you need to choose a point.
Exactly, you need to choose a point, but there are going to be a lot of formulae of this type, and it's very important to remember that the x's are playing different roles. And that's been a major sort of psychological stumbling block, and of course a lot of conceptual errors. So I'm really going to go over this many times this afternoon. And then this morning, then this afternoon, the whole game will be to try to understand the action of G on X, which is going to be extremely subtle, via the action of X on X. So this thing will be the Ihara action, and this will be the action of the motivic Galois group. So that's to this morning, and this is this afternoon. So that's where we're headed. So now let me recap what I did last time. So we had a manifold, which in this case is P1, the complex points, P1 minus 3 points. And for now, let me just take any base points, or, as I defined last week, tangential base points. So let me remind you extremely briefly what that was. That's just a tangent vector at 0 of C in which we've removed 1, or a tangent vector at the point 1 of C minus 0. We could take a tangential base point at infinity, but I don't need to. So then we had the fundamental groupoid, homotopy classes of maps from one point to another, or one tangential base point to another, and the groupoid multiplication is this one. And then I defined for the group, and for the fundamental group and the groupoid, and with tangential base points, what the Maltsev completion was. And the Maltsev completion was simply called the Betti fundamental groupoid. That's just a name. And so what it gives is exactly the same picture, except with a superscript B for Betty. And so now these are, so what is this? It is, so pi1 Betty MXY is a pro-unipotent groupoid scheme. So that's just a lot of fancy words over Q. And so this thing here is actually a morphism of pro schemes. So it's some kind of projective limit of algebraic varieties, okay, defined over Q. And so what was the construction? Let me recall very briefly what the construction was, or one of the many constructions was via its ring of regular functions. And so what we did was to look at, first we take the group ring, sorry, not the group ring, you take this thing, it's so easy to make these slips of the tongue, I defined the image of the augmentation ideal in this thing by viewing it as a torso over the fundamental group based at X. Okay, so last time I did that by choosing some path. It's very explicit, you don't have to do that. Then we dualize, so we look at, in other words, we look at functions on this thing which had unipotent monodromy, so I explained all of that. And then we take the projective limit. Okay, so that's a reminder from last time. We won't need that so much this time. Then, so that's, yeah?
Inductive limit?
Oh yeah, so, thank you very much, yeah. Yeah, thank you. Yes. Absolutely. So now then, so that's Betty, and then Durham. Durham fundamental group. So we had Q of E0, E1, which is a graded Q vector space spanned by words in the two letters E0 and E1. So it's graded if we give E0 and E1 degree 1 each. So this is a graded comma commutative Hopf algebra. So let me remind you that the multiplication was given by the shuffle product. Which I denote by Shah. And the co-multiplication was denoted by delta C, I think I wrote delta C, and this was the deconcatenation coproduct. So slicing up a word in all possible ways. Okay, so then the Durham fundamental group is
Can I ask, you made a point about that comma. You mean it's graded and commutative?
I made no point about it, I just read out the comma. Absolutely, yeah.
Okay.
It's commutative.
It's genuinely commutative.
It's genuinely commutative. It happens to be graded as well. It's not graded commutative. Yeah. That was the point of putting the
What's the
comma.
point of the comma? I suddenly realised.
Yeah. Okay, so the de Rham fundamental group is now a genuine group. It's an affine group scheme. So it's determined by its ring of regular functions. What's mine? And no need to specify base points at this juncture. And so it's just Q of E naught E1. And so, of course, the pi 1 de Rham is just a spec of this thing. So it better be commutative when I write the spec. Oh yeah, and so this thing again, well, actually no, not again. This thing is a pro-unipotent group scheme over Q. So last time I explained that that's a functor from commutative unitary Q algebras to groups. But really, the thing that it's really just this Hopf algebra, which is defined over Q, and the fact that it's pro-unipotent means that this is a filtered Hopf algebra that is graded. So it's probably better to think in terms of. I much prefer to think in terms of Hopf algebras. Okay, so and the point was that this thing should be thought of as abstract iterated integrals on P1 minus 3 points. So every word in these symbols should be thought of as an iterated integral. So more concretely, we had omega naught, which is indexed by E naught, and omega 1 indexed by E1. And every word, EI1, EIR, is going to correspond to an iterated integral omega I1, omega IR. And so we can think of this as an abstract iterated integral, if you like, a function on possible paths of integration. It's a function on paths. And what I explained, but didn't prove last time, was that this thing only depends on the homotopy class. I should specify, of course, relative to its endpoints of gamma. So it gives a genuine function on the fundamental groupoid.
How do we know it's homotopy invariant in this generality?
How do we know? Because so I didn't prove it. The general theorem is that a linear combination of forms is homotopy invariant if, as a function on the space of paths, it's constant. Okay, so that means that the differential on the space of paths is 0. So it's h naught of something. The differential in the space of paths is given by the differential in the bar complex. So the general answer is that this should be an h naught of the bar complex. In this case, the differential of the bar complex differentiates each term individually, but they're all closed, so that's just 0. And it takes successive wedge products of differential forms. But our manifold is one-dimensional, so the wedge product of any of these things is trivial. So had I had more time, I would have proved this by hand. It's you can just do it by hand, yeah, by Stokes' theorem. It's very, very easy. And using the fact that the classical fact that a line integral is an ordinary line integral is homotopy invariant if and only if the form is closed. So I apologize, I didn't give the proof of that. It's not very difficult. Had there been more time, I would have done that. Okay, so then we can actually integrate these things on paths. So I can take a path in M from X to Y. Oh, I forgot to say something very important. My apologies. Something very important here, I completely forgot to say, is that there's a natural map so this is really important. from the actual fundamental groupoid to the Q points of the Betti fundamental groupoid. So sorry about that. So that's I'm going to use this right here. Pi 1 Betti MXYQ. And then I can just integrate it, and it's going to give me something in Durham. Actually, I'll be a bit more precise here. Durham of P1 minus 0, 1 infinity complex points. And so we take a path. Let's compute the integral. So we take a path from x to y and just send it over here. And so this is, so gamma is going to define a HOM from this to complex numbers. In other words, that's precisely an element in the complex points of this. So we want a HOM from this to complex numbers. That is a map from words to complex numbers. And that's precisely the map which sends this word to the iterated integral along our chosen path of the corresponding one forms. And so this thing can be represented as a series, of course. It's a function on all words. So it can be represented as a generating series, integral over gamma EI1 EIR. And so last time we computed the image of the straight line path. So we had DCH in pi 1.
Is it EI1 dual times EIN dual?
Yeah, so I'm going to be very sloppy. I'm going to be very sloppy about, so strictly speaking, whenever I write generators of Betti or Durham, I should have dual variables. In practice, it's a nightmare to type this because so I do what everybody else does, and I just give it the same name. Yeah.
But then you're sort of taking graded duals.
Yeah, don't worry about it. It's okay. Yeah. So I will introduce it. I will use this notation a little bit later for a different reason. But this is. Yeah, I write. Yeah, it's okay. It's okay. Strictly speaking, yeah, one should say something. Right.
When you write Q of E0, E1, you're using the notation for non-commutative polynomials.
Yeah.
And you
I'm using this is a non-commutative polynomial.
It's commutative.
Sorry?
Well, you're putting the shuffle multiplication on it, so you're making a commutative ring out of it. It's just a notation that's confusing.
Exactly, this is a standard notation. This is also a
Non-commutative
standard notation.
Well,
This is also standard.
we would write it the Coffrey coalgebra.
Yeah, exactly, it's the Coffrey
We
coalgebra.
would write TC
Don't you like that?
E0.
I could write TC and view it as yeah.
So the thing to keep in mind is that it's not generated by the EIs. It's generated by words in the EIs
Absolutely,
and
yeah.
shuffle multiplication.
Yeah, absolutely. So yeah, absolutely. As a vector space, it's spanned by words. As an algebra, it's spanned by certain types of words. Call them Linden words or
And with shuffle multiplication.
with shuffle multiplication.
So-
Yeah. Yeah, so I believe this is a standard notation as well, and identifying the things with the dual. Yeah, I'm going to do that. Right. So it really makes no difference at all. I've tried in papers to be careful about this, and you give up after a while. It's just, okay. So we had the trois chemins. So, which was the straight line from, so 1, 0 to minus 1, 1. So we had the point 0 and a tangent vector of unit length 1 in that direction. And that was the picture, and the trois chemins is just a straight line. The straight line 0 to 1. And we computed last time that, so this path, if I do this integration thing, I get its image in pi1 Durham, which is some infinite power series, non-commutative single power series. And we computed this last time, and it gave sum over the words in 2 letters, zeta WW, where the zeta was some regularized version of multiple zeta values. And this is the Drinfeld associator. Okay, and then the final thing that I finished on last time was Chen's theorem, which is much, much more general than this. And I didn't state it in complete generality, I just said what it gave here. And it's that after tensoring with C, these rings here are isomorphic. And this isomorphism uses the integration map, and therefore very heavily depends on the choice of base points. Okay, so this is, I wrote last time, at the end I just wrote isomorphism. I should have been a bit more precise. It's an isomorphism of pro schemes over C. And the important thing to remember is that it really depends on X and Y.
Isn't the pro scheme a scheme?
Yeah. Absolutely. Yeah, just because of the habit of saying pro-unipotent, and then it's good to keep the pro in there somewhere. Yeah, I keep the pro because when you want to make this an object in a category of motives, then it's very important to remember that it's a pro and it's not an actual object. It corresponds to an end object. Okay, so now let me go backwards a step to P1 minus 0 infinity. So here we have base points. So I'm going to take t an arbitrary base point. Just take a tangent vector 1 at 0, and then some random point t in C star. And so just to recap quickly how to compute this. Obviously this is just homotopy equivalent to a circle, so this is free. One generator, the ring of integers, the ring of regular functions on Durham is isomorphic to the same thing as before, except we've only got one generator instead of two generators, and now I like to think of E naught again as corresponding to dz over z, which is the one form defined over Q on this thing. And pi1 Durham, P1 minus 0 infinity, on R points, where R is some commutative unitary ring, is just a set of group-like invertible series for this different coproduct which I defined last time. It's the coproduct for which, in this case it's kind of trivial, for which x naught is primitive. So a stupid exercise which you can check, is that this Hopf algebra, Q E naught, with the shuffle product and deconcatenation coproduct, is isomorphic to a polynomial ring in one variable with multiplication product, and for which the element, the generator x, is primitive. In fact, I remember I did this last time because I computed the maps of completion of Z. So. And so what this means is that pi1 de Rham, so this is just the additive group we saw last time. So pi1 de Rham of pi1, p1 minus 0 in infinity is just the additive group. Okay, so yeah. So why am I worrying about this case? I just really want to argue that this thing is when we're going to let t be equal to 1, and I want to argue that this thing is trivial in some sense. The reason is because when everything becomes a motive, this part's pretty delicate and it's not entirely satisfactory, I must say. So I'm going to try to convince you that this thing is trivial by sort of pulling the wool over your eyes. So let's compute the periods of this thing. So let's look at, we have the fundamental group, again, mapping to Betty. And then I want to send it into de Rham. Complex points. Sorry, I'm not being very consistent here, but much rather write P1. Okay. So we take a path, and same thing as before, compute the formal power series. So this time it's iterated integrals of words in the one form, but we only have one form. It's dz over z. So the only iterated integral is this. Is the single word of length n in one letter. So I'm going to integrate along gamma. So this is going to have n factors, and it's going to be indexed by e naught, the n. So gamma de Rham is this generating series. So now recall from the lecture 1 there was a shuffle product property, which I think was property 2, 3. I think it was probably 2 last time. Shuffle product was property 4. I'm lucky. So this is just 1 over n factorial integral dz over z to the n. So there's an n factorial that comes out when you shuffle n things together. Times e naught to the n. And this is equal to the generating series 1 over n factorial of this integral. But we know how to integrate dz over z from basically 0 to t. There's this regularization business for the tangential base point that I explained last time. In fact, we did this integral. And so it gives log t to the n, e naught to the n. And of course, here we see very clearly that it depends on the homotopy class of the path, because log of t is a multi-valued function, and it obviously depends on the base point t. And in fact, this thing's entirely determined. In fact, all the periods are determined once you know the single period log t. Once you know log t, you know everything, you know the whole story. And so here I'm going to really I'm cut a long story very, very short. That when t is 1, we have log 1 is 0. Okay, so I hope that's sufficiently convincing. If I take the base point t equals 1, then log of 1 is 0. And so this series just becomes trivial. And so I want to say this sort of motivates the fact that the motivic fundamental group that we'll come to later, with base point, tangential base point 1 at 0 and endpoint 1 is somehow trivial. So to actually make sense of this, I have to talk about Kummer motives and really calculate something. And to make use of this for the fundamental group of P1 minus 3 points, there's a pretty tricky passage that's kind of fiddly and not ideal. So I'm really cutting out a whole quite subtle part of the story.
Can I ask you a question before you? Okay, I
Sorry?
thought you were going to erase that, but you didn't erase it. When you write dCH is sum of zeta WW,
Yeah.
you're actually considering W in the commutative Hopf algebra?
No. It's just a formal power series.
Yeah, I understand, but in which space?
In
E0, E1.
so this is a recap from last time. This is in the space. This is an element in the space, or in fact R,
Pi 1 dr, right?
of elements S in R. So again, I'm slightly abusing my letters, but it's seriously irritating to have.
I understand that.
So
This-
invertible such that S is group-like.
Yeah. As a power series, I'm fine with the definition. It's how you multiply them that I'm asking you, like when you want to do the associated relations.
I'll multiply them by concatenation.
Okay, but so they're not in Q. But I'm confused because you're saying they're in.
The majority is not in notation.
You're saying they're in pi 1 of dr, right?
Yeah.
And pi 1 of dr.
Has a different. The problem with has a different multiplication, which is and a different coproduct. It's dual to the other one.
Okay.
But I hope I was clear on this,
This is
last
completely
time.
clear. It's just how you multiply the series.
Yeah, it's just concatenation product. So I explained this last time, that S dot T, the multiplication of S and T is concatenation.
Oh, you're in the dual of QE0, E1. That's the point. It's pi 1
So I
dr.
don't know, it's maybe,
You're in the dual of QE0, E1. You're
yeah,
not.
this is a dual.
Okay, fine. That was the thing. Which also looks like QE0.
When people use brackets,
Yeah.
I think they are polynomials, so it's the concatenation product. So actually, the underlying guy is always
Yeah.
a polynomial.
Yeah.
And co-free.
Yeah, I agree with you. There's, well, I don't know where this notation comes from, but in my mind it seems to be fairly standard in this context. It's the underlying vector space is the same one, but
Right. Okay, it's clear now.
it's fine. It gets more confused. It does get confused. Actually,
Yeah.
it's not confusing at all at this point, because when I consider Durand, it's always a completed group ring in some letters, call them X0, X1, doesn't matter. And the dual thing is always this.
Okay.
I will never,
Call this
well, I maybe sometimes take the associated weight graded of this, which has the same notation. That gets confusing.
Okay, but you'll never call X's E's, so. Okay, so we know what side we're on.
No, I will call X is E, so I'm not being very consistent about that. Sorry about that.
Okay.
Don't worry about it. It'll work out.
Okay, it's clear for now.
It'll work out. Okay, so now, so that was all recaps from last time. Now I want to actually study the automorphisms of the Durand fundamental groupoid of P1 minus 0 on infinity at certain base points. So last time I introduced this notation 0, 1, which is slightly sloppy. and I'll explain in a minute again what I mean by this notation 0, 1. Okay, so what we had is two tangential base points, one at 0 and minus 1 at 1. Okay, and what I'm going to do is now write. Have I skipped something? Yeah, I'm now going to write from now on pi xy for pi 1 deram p1 0 1 infinity base points x and y. So x and y are going to be, I'm just going to write 0 and 1. Instead of having to write out all this heavy notation every time, I'm going to write 0. So when I write 0, it means the base point, the vector, the only vector we consider which is based at 0, and 1 is going to mean the vector at 1. Okay? So this is because I don't want to write huge formulae all the time. Of course, Poirot and Durand didn't depend on the base point. So why am I putting this notation? Well, that should become clear in a minute. But all these pi xy is in fact the same thing.
Sorry, what is this notation? Xy belongs to?
0, 1.
Ah, this.
So there are four objects.
Okay.
So what do we have? So I'm describing the object x, whose automorphisms I want to compute. So what is the object? It is 4 schemes. Pi 0, 0, 0 pi 1, 1 pi 0, and 1 pi 1. And they're all the same. Okay, so each x pi y is isomorphic to the set of series. Oh, sorry. So I'm going to view it as a functor on commutative unitary rings. If you don't like this, you can put Q everywhere in the whole of the next section. It doesn't change anything. But I want to view it functorially in the coefficient ring. And so now, actually, I am going to put... I was very lazy about this before. I am now going to put upper indices for this side, for a stupid notational reason. Such that the series is group-like. Okay, and again, I'll just remind you yet again.
It's a unit, isn't it? Understand?
This means invertible. So for a power series to be invertible, it's sufficient for the first.
You just use a cross.
Oh, sorry, am I being overzealous?
I think that's the source of greatest confusion.
Oh, really?
What did you?
Start. Okay, it looks like an X though then. You prefer this?
Oh yeah.
How about check for a dual?
No. This is the invertible elements.
I think maybe the constant term should be gone.
Of a group like
If you prefer. This is invertible elements in the ring. That's
How
okay.
about constant?
That's equivalent.
Yeah.
It's equivalent because there are no idempotency.
if you have a group like element, the constant term is either 0 or 1.
Okay, just this equation implies it has to be 0 or 1. So I just mean make sure it's not 1.
So couldn't we move the E0 and E1 up there to upper 0?
Yeah, I have to edit all my notes. Sorry. Just draw. This is.
Okay.
Had I written all my talks in advance, I would have been more consistent about notation. And so the dual thing is the same old thing. So now I will put the zeros upper here and lower here. I actually prefer to do it the other way around. The reason why I put upper here will become clear in a minute. It's not for any. It's just because just to make the formula look a bit nicer. And so what I want to do now is write. So we're going to have elements like 1, the unit, the trivial power series, and that 1 can appear in 4 different places. So there are 4 different copies of 1. So write 1xy or E0xy, etc. for the corresponding element in x pi y. So here, of course, E0 is actually not an element because it's not group-like, but so I should really exponentiate. That is a group-like power series. Okay, so this notation is applied not only to the to these groups, but also to the elements in the groups. So we just have 4 copies of the same thing. And then the second structure that we have is a groupoid structure. So last time I drew this this diagram, so we think of these 4 different groups as sitting on these arrows. This is a path from 1 to 0. This is a path from 0 to 0. And this is a path from 1 to 1. And so associated to every arrow in this diagram, we have a composition law. This is for all x, y, z in 0, 1. So there are 8 different multiplication laws encoded by this diagram. And so this thing is a morphism of schemes. So we don't really care about that.
How are you exponentiating E0xy?
Sorry?
E0, so at the top of that.
By the standard formula, 1 plus E0 plus E0 squared over 2 factorial plus.
Isn't there a problem that it's path in a groupoid rather than a loop?
No. Each pi is a group.
Oh, so you're using it.
Each pi is a group of group-like formal power series.
Okay.
So exponential of E0 is by definition 1 plus E0 plus E0 over 2. Sorry, squared. By definition, and that's a group-like element. It's the exponential of a primitive element. So that's the thing. Each pi is a group, but I'm not going to use. We're not going to use that group structure. Well, not immediately anyway. Well, yeah, no, we will a little bit, but not much.
So, a while ago, the Durand fundamental group did not depend on base points.
Yep.
So now you've just put symbols xy in there.
Yep.
Purely formal meaning.
There's 4 copies of the same group.
And so what's this composition supposed to be that we're not going to use?
Multiplication of group-like series.
So that's just the group multiplication. In
So yeah, but with the rule that you change the little indices. That's it. So the reason why it's
So
Yeah,
it's
no.
constant groupoid.
sorry, it's a constant groupoid. Yeah, it's the constant
Constant
groupoid.
groupoid.
Absolutely, it's a constant groupoid. The point is that the Durand is I need that. The Durand is constant, but it's the action that changes depending on base points. And so, in some sense, the Durand is a reflection of the motivic thing, which depends heavily on the base point. But the Durand functor is not fully faithful. It loses some information. And we have to keep track of that information with the indices. Okay. That's really what's going on. Oh yes, and then the next thing is inertia, which I glossed over a little bit. Inertia So there's a natural map from P1 minus 3 points embedding into P1 minus 2 points. Okay? Where you forget used inclusion. This map is extremely subtle and is not at all understood. So that's not just a tongue-in-cheek comment, it's really genuinely a hard to understand thing. Remember the consequences of that. That's not the map I'm looking at. I'm not looking at the natural map. I am now going to look at the local monodromy map, which goes in the opposite direction. So this does not come from a morphism of schemes. It goes the wrong way. So it's a map from let me put the base points. Let me just put the base points now just for concreteness. Into pi naught naught. So of course the natural map goes from pi 1 minus 3 points into this thing. This goes the other way, and it's you think of it as a little, if you have 0 and 1, if I have an element of the fundamental group here that's very small, then I can send it into P1 minus 3 points, because it's not going to touch. It's very small and it's not going to come near the 1. So there's an idea of a notion of local monodromy around the point 0, and it really doesn't see what's happening at the point 1. And you can check that actually this thing does make sense. And so what it does, it maps group-like elements in this power series to group-like elements in this thing. And what it does specifically is it maps the exponential of E naught to the exponential of E naught. If I'm to be consistent, I should write this. So just the obvious thing that a series in one variable is in particular a series in two variables. Again, to make motivic sense of this, one has to be a little bit, has to work a little bit. What's the dual thing? The dual thing is this to O of pi 1 to RAM with the same, with a single base point, and it maps Q E naught E1 to Q, sorry, it's lower indices now. And it basically just sends E1 to 0.
Can I just be obnoxious again?
Sure, yeah.
Why are you writing x of 0 E naught 0 instead of putting the zeros on the outside of the x?
Same
Because
thing.
E naught doesn't, E
Same
naught
thing. How
doesn't
could
belong
X
to
take-
0 pi 0, right?
Sorry?
It's not grouplet. E naught itself. E
It's
naught
not
does
grouplet,
not
no.
belong to 0 pi 0.
No,
So x E naught belongs to 0 pi 0.
yeah.
So why didn't you write 0, x E naught 0?
It's like completely identical.
Okay, so you're not meaning
How do I
that,
take the exponential and leave the object that I'm in? I mean,
Well,
it's
look-
tautological that it has. Yeah, if you
no,
want
my
me to, I
test
can.
is 0 E naught 0 doesn't really exist.
Oh, I see what you're saying. Yeah, okay.
Just
Yeah. Right. Well, it does exist. It exists in this ring.
Yes, but
So it
it's
doesn't
not
satisfy the
0 pi
condition,
0. Okay, I mean, just being really clear, okay?
Right, okay, so that's the local inertia. So we have the image of P1 minus 2 points sitting inside P1 minus 3 points, just included. And there's the same story at the point 1. In other words, what I'm saying is that there are loops in P1 minus 3 points, trivial loops that just wind around 0, or that just wind around 1. And they are the images of something where the other point played no role at all. They're going to be trivial. So definition.
So the last map you wrote, the map on functions.
Yeah.
So you got E1 goes to 0. That means any word with an E1 in it goes to 0.
That means any word with an E1 and it goes to 0. Yeah. Yeah. So E naught to
That's a map
A1.
of rings, but with the
Well, no, it goes to, it goes to E naught to the A, R maps to E naught. This thing.
No, that's E1 goes to 1, surely.
Oh, sorry. Yeah, of course.
You're keeping only one variable.
Yeah. So basically, W maps to, thank you, yeah, W is up to 0 if E1 is in W. And then
This
E,
multiplication is shuffle multiplication. You're right.
that's it.
Sorry.
E naught to the n goes to E naught to the n, and W goes 0 if W has an E1. Yeah.
But W is considered as shuffle product.
Yeah. So this is
This is commutative ring. I'm
this
sorry.
is
So
almost
that's
a
just
shuffle
me.
product.
Sorry.
The best way to think about that is it's a map of co-free co-op.
That's one way to do it. Yeah.
It's a map of co-op.
Absolutely.
Right.
And yeah, it respects the shuffle product.
Right.
Okay, gosh, I'm getting a bit behind. So now this is the whole point. So this is the object X I was referring to earlier. It's the data of these four groups, all the same as each other, with all these structures. And the group of automorphisms is going to be called V. So I use the notation in Dolin and Gonchow's paper. Those, I should specify that Dolin and Gonchow's conventions are exactly the same as mine, except all words are flipped. All words are reversed. So I look at the group of automorphisms preserving these three things. So what does that mean? Every element alpha in the group of automorphisms is by definition a 4 tuple of automorphisms x alpha y, which maps pi xy to pi xy. So this is again a morphism of schemes. It's not so important. And xy are any indices in 0 and 1, that's why there are 4 of them, such that it respects the groupoid structure. So what does that mean? That means that every time we have a composition law, where the multiplication is concatenation and fiddling with the indices to make sure you land in the right thing. So every time you have a concatenation law, then all these automorphisms respect y, z, respect that structure. So it's a commutative diagram like this. So this commutes for all x, y, z in 0, 1, so there are 8 such things. And first of all, so it's got to be a morphism of groups, so it's got to map alpha on the unit on 1 equals 1. That's because it respects, these are groups, remember? Groups of formal power series. Needs to respect the unit. And then there's a final condition, which is that the inertia condition is respected. So I here try to hand-wavingly persuade you that this thing, p1 minus 2 points, is trivial, and its automorphisms should be trivial. In other words, if we think of ultimately the motivic Galois group is a Galois group of periods, transcendental numbers.
So, what
Log of
automorphism of a groupoid,
sorry? Yes.
not autoequivalent.
No. This is just I haven't finished the definition yet, but it's literally automorphism.
So automorphism, which is the identity of the objects. The identity mapping on objects.
Yes.
The objects are x, y.
Yeah. If you want to think of it as categories, yeah. There's no okay, I need to press on a little bit. And so the other condition was the inertial condition, And that's it, x alpha x acting on x e x x is the action is trivial. So I tried to persuade you this fact. Let's accept it. So in other words, we want the group such, the automorphisms which act trivially on local monodromies. Okay, so now a result that I'm actually going to prove. Proposition. This is the key thing. So I want to describe this automorphism group. And the point is that the map V to 0 pi 1, where we take an element in the automorphism group, we call it, it's a 4-tuple of automorphisms, and I look at 0 alpha 1 acting on, oh sorry, I've done something very stupid. My apologies. So please correct this. This is not xy. This is xx, of course. Sorry.
Oh.
Maybe that was the question. Right, because x pi xx is a group. Pi xx is actually is a group in this groupoid. So it needs to preserve unity. Sorry, that's a
Is
typo.
this automatic because it's a formal scheme and this is the only point? Or am I
I
missing?
don't think this is automatic.
It's not. Oh, even if it's a formal scheme, it could still slide formally. Oh.
Sorry, so I'm really sorry about that. That was a complete typo. I hope you corrected that.
So the maps alpha x y, they're just maps of
Well, it's not
sets to begin with, not groups or anything.
alpha maps of morphisms of schemes.
Not a group scheme.
But no, it's a morphism. It's a groupoid. So
Yeah, but the pi.
so here, so this is a group. So in fact, so 1 times here. Let me write the equation. 1 times 1 equals 1. So alpha 1 times alpha 1 is alpha 1. And I'm saying that in fact alpha 1 has to be equal to 1.
But there
I'm
is
sorry,
an
that
element
was
called
that's
x1y.
Sorry?
There is an element called
There is an element called 1xy, which you used to think of as the path from x to y.
And you don't
That's a highly non-trivial path. That's the
specify what
Greenfeld
alpha does.
associator. You don't have no idea how it acts on that. But the path from x to itself is 1. It's the unit. It's something that satisfies 1 times 1 equals 1. So alpha 1 times alpha 1 equals alpha 1. And it nearly determines alpha 1, but not quite. So we have to impose that alpha 1 actually equals to 1. Right? Right. So
This diagram simply says this alpha is a factor, yeah? That's in my understanding.
alpha is a functor.
Function of categories and
Which is
In terms of categories, yes, it is. Yes. Yes. If you think of pi as each group, what is it?
Yeah. And what is the second condition?
This thing here.
It's not condition.
This is a condition, yeah. This is that the local monodromy is preferred. It's acting trivially on a small part of the groupoid. It's a very small part of the groupoid that comes from P1 minus 2 points. Absolutely minuscule part. And it needs to act trivially on that. And that's going to be really crucial. It looks like nothing, but it's actually going to be very, very important. Right? So, so the element 1 identity in from 0 to 1. So that this is should be thought of as the path from 0 to 1. This is the Greenfeld associated. It's highly non-trivial. It's going to be acted on in some way. We don't know how. And in fact, if we know how the automorphism acts on a single element, then we know the entire automorphism. So the point is that this is an isomorphism of schemes. But don't forget, this is also a group. But we're not considering its group structure here. Absolutely not groups. Okay, so proof. So let alpha in V, and let us write A, let us define the element A to be the action of alpha on the path from 0 to 1. So what's going to happen is that this element A, is going to determine first the action of alpha on the copy 0 by 0. So first we have to work out how it, from this information, we have to work out how it acts on 0 by 0. And from there, its action on 0 pi 1. And the reason why you can go from here to here is because this is a torsor under that. Okay, so now how do we compute the action on 0 pi 0 from the data of this single series A? Well, we observe that the Lie algebra of 0 pi 0 is the free completed Lie algebra on two generators, E00 and E100. So that means that it's enough, it suffices to know the action of A on something corresponding to these elements. So to understand the action of A on 0 pi 0, it suffices to know the action of alpha on the two series exponential 0, 0, 0 and exponential 1, 0, 0. From that you get everything. Okay, so that's the first step is to do that. I'll do that now. I need to accelerate it a bit. Okay, so how do we do this? First equation is 0. So 1 equals 1 times 1. So 1 is 1 times 1 in this groupoid is exactly this equation. So you have to think about what it means to be a groupoid in groups, but this is exactly. So alpha, this is an actual genuine group element, so alpha acts trivially on this by the equation up there. So if I apply alpha, I get 1. Alpha of 1 is 1. Alpha of 1, 0, 1, well, we've given it a name, that's A. And alpha of this thing, we just don't know. So it's alpha 1, 0, 1, 1, 0. So we get our first equation. And that means that in this group-like formal power series, the element 1 alpha 0, 1, 1, 0 is the inverse of the series A. Okay, next, so now we want to use the fact, I want to use the inertia at 0 to get some information. So what we know is that 0 alpha 0 x E0, 0, 0 equals x E0, 0, 0. Right? So that was one of the assumptions. And so what we want to understand what's going on at pi 0, 0, okay? So as I said, to understand what's going on at pi 0, 0, we only need to know what's happening on this element and this element. And then it's determined. This element we have for free by inertia. This element we have to compute. So the way to compute this is to send it over to 1, where it's going to become an E upper 1. But in E upper 1, at the point 1, it corresponds to the inertia of 1. So we're going to do a loop around 1 and come back. So we send, to compute E1 0, 0, we send it to 1 and come back. So that's what I'm going to do now. So now inertia at 1 is going to tell us that we know this equation, which tells us something about the upper ones. Right? And I want to bring that back to find about something about E upper 1 with lower naughts. So what's the equation relating these two? Well, x E1 lower naught is 1, 0, 1, x E1, 1, 1 lower naught. So it's exactly this picture. And now let's apply the automorphism to this thing. So that means that naught alpha naught x E naught 1 naught equals alpha of 1, which by definition was A, this thing, which doesn't move by inertia, and 1, 1 naught, which by this equation is the inverse of A. In other words, alpha acts by conjugation. It acts trivially on this element, it acts by conjugation on the other element. So let's give this action a name. Call this map angular brackets sub naught for the action corresponding to the element A at the point, on the single copy pi naught naught at naught. Okay? Now, so from having computed that, the action at pi naught naught, then it propagates to all the other 3 copies. So let me just explain how this action propagates to 0 pi 1. And then the rest you can imagine. Okay, so now so how do we compute the action on an element in 0 pi 1, which is what we're really interested in. Then we can write G, let me write it G naught 1. So G naught 1 is, by definition, G naught naught times 1 naught 1. So now if I apply alpha to it, it's the action on alpha on the copy of G in pi naught naught, which we've just computed, times the action of alpha on 1 naught 1. And that, by definition, was A. So the action on the copy 0 pi 1 is the same as before, except we have an extra concatenation on the right. And so if you work this out, the element A determines the action on 0 pi 0, 0 pi 1. We've done that. The other two I leave to you. 1 pi 1 and 1 pi 0. And you check that by working all these equations backwards, every such element A, in fact, determines an automorphism. Alpha. So that's the end of the proof. Okay.
How do I know it's not trivial?
How do you know it's not trivial?
The kernel. I mean, how do I know that the
It's not, but definitely it acts on one. So you take an extremely complicated series, it acts on one and gives that series back. So, no.
Right.
Okay, so this is the thing I was saying that's confusing. We have automorphisms of some object X, which is this groupoid gadget, and it's isomorphic to itself. So this is where the trouble begins. So let me just recap. So we have this group of automorphisms of the fundamental groupoid acting on this part of the fundamental groupoid. We can forget about the rest because we know it's completely determined by the action on this piece. So action by automorphisms. And the proposition tells us that V is isomorphic to 0 pi 1.
What do you mean by every such A? Every such A.
Every
What are the
group-like
A's?
formal power series.
Every invertible
Group-like.
formal power series. Group-like formal power series. Okay.
So if you like, you can take Q points everywhere in that argument. It doesn't change anything. But it's nice to think of V as a group scheme, as a sort of a functor on commutative unitary rings. Just take, if you don't like that, just take Q. It's the same thing. Okay, right. So that's that. So in order to let that sink in, I am now going to give about 3 or 4 different variants of this action, and give lots of different formulae. And all these formulae occur in the literature and are used a lot. And I will go between all of them and show that they're all equivalent. And then that'll be it for this morning. So, sorry, I've got to say definition. Sorry, whoops. Not yet. The definition is the Ihara action is the left action of V on O pi 1, but we identify V with O pi 1. So that's what I want to call the Ihara action. Okay, so now let me, I want to just play with this definition and consider lots of different variants of this formula. So for now, at least, we can think of at least 3 versions of this action. Possibly even 4. So the first one is very explicit. So remember that O pi 1R is the set of group-like formal power series which are invertible and group-like. And so then the Ihara action gives us a map from this cross itself to itself. It's a well-known formula. So I'm not entirely sure, I have to confess, I'm not entirely sure about the history of this. Some of these formulae in Drinfeld's work, I don't know exactly who did what at which time. So then we get a map O pi 1R cross O pi 1R goes to O pi 1R. So we take a group-like series in 2 letters, and I take another group-like series in 2 letters, and we use this formula. So this formula says that the action is given. First, what you do is you take your group, your series here to the 0 action. This just sends E0 to itself, and E1 gets conjugated by the element A. So that means you take E0 doesn't move, but E1 gets conjugated. Oh, sorry. Upper 0, upper 1, upper 1. Okay, but it's not finished because we also need to concatenate on the right. So times S, not E1. So that's the action of one series on another. Okay.
So this is twisted Magnus product. This is old.
Yeah, this is old. Yeah, it's just the automorphisms of something. Really, when I'm saying something very banal, we're just computing the automorphisms of an object on itself. It always has this kind of general shape. You can do it to any object under the sun. Also, a point to make is that my conventions are slightly different. I'm acting on the right. Some people use different conventions, but at least I'm going to be consistent. Okay, so that's one formula you see a lot. Now let's look at the Lie algebra version of this. So the Lie, I said it already, it's the completed free Lie algebra on two elements contained in the ring of formal power series E0, E1, it's a set of primitive elements. And so I can actually look at the action, the infinitesimal action of this thing. So I just want the Lie algebra acting on the left. In power series. So how do we do this? So if we take F in this Lie algebra, then what it acts on this by derivations. So we get a derivation, often written delta sub F, E0 so this is the infinitesimal version. So think of this as the infinitesimal of this action A0, this delta F thing. So what it does, so A0 acted trivially on E0, that means the infinitesimal version, it descends it to 0. And in the infinitesimal version, the action on E1 was conjugation. So as we all know, the differential of conjugation of big add is little add. So it's just the adjoint action of F on this commutation by F. And then, so we haven't finished because there's this concatenation on the right business. There's this concatenation on the right that I'm just about to erase. So what we get is an element F, a Lie series, acting on an I can look at it just on an individual word, maps to the derivation F acting on W plus concatenation of F on the right of W. So in fact, you can restrict this to the subset of primitive elements, Lie subalgebra, and you get this thing, again very famous. And of course, when you have such an action, you want to anti-symmetrize it. So if you anti-symmetrize, we get what's called the Ihara bracket on this thing. So it can be an anti-symmetric bilinear product, and it's written F comma G, F circ G minus G circ F. And then the third variant I want to consider that's going to be extremely useful. Because in fact, for computations, these things are extraordinarily inefficient. It's much better to look at the dual. So obviously, when you have something like this that's functorial in R, we get a dual coaction. So now let me in the remaining 15 minutes, would it be okay if I went over a tiny bit?
Ask the other ones.
Is that
Yes, sure.
to save extending into the exercise session? I think, is that okay if I just have an extra 5-10 minutes?
Yes.
Got a lot of questions. Okay. Lots of vigorous nodding of heads in the audience. It's a resounding yes.
So is this new bracket related to what Leila explained?
I imagine so, yes.
Can I, just make a remark. If you're looking at R of E0, E1 as the universal enveloping algebra of Lie,
Yes.
what you're doing is you're describing the multiplication in the universal enveloping
Yes.
algebra on series in the X and on 2 Lie elements and on 1 Lie element.
Yeah.
In series. But you're using different symbols each time, but it's really just always the multiplication.
It's always the same thing. I'm going to write the same formula. I've written the same formula 3 times, different guises.
And do you have
And I'm going to write it in 2 more guises.
I've always wondered,
Yeah.
just, do you know the general formula for multiplication of R cross R?
R
Of 2
cross-
elements in the universal enveloping algebra.
The
But we
universe-
know exactly how to put together 2 elements of Lie and how to put together 1 element of Lie in 1 power series.
So
And
what
how
I'm-
to put together 2 elements of power series that are X of a Lie element. But I don't know a formula if I take
I'm just about to write down a formula that does exactly that.
that in the code.
It's not in any. No, that's
Okay.
no, that's in this setting. So it's not anywhere. So okay, what I was going to say now is that I want to tie in with Goncharov's coproduct, which was derived in a completely different way using framed mixed-Hodge structures. It's a very, very long proof. It's about a 60-page paper. I'm going to derive it in a couple of steps from this. In order to do so, I'm going to introduce something that's not in the literature anywhere. I apologize. It's the first part in the talk. We can't read this anywhere. And then I'll explain how to do that bridge, and then it'll answer your question, I think. Okay. So I'm now going to introduce something slightly different. So yeah, I apologize for being off the record. Linearized Ihara action. So I just took the name I thought up. So remember, we have an antipode S. So what it did was it takes words. Oh, sorry, it's very hard to do these upper indices consistently. Dug myself a hole. So -1 to the R, and it reversed all the letters in a word. So denote this by star. So the standard notation from antipode S. Here I just want to call this operation where you flip a word and put a sign by star. And now follows the most idiotic remark. So that if F is in Lie O pi 1 of R, contained in, as Zeta points out, the universal enveloping, then F star is minus F. Right? The antipode acts by -1 on Lie elements. So now I'm going to do something, a bit of trickery. In the Ihara action, we have F commutated E1. So F comma E1 is F times E1 minus E1 times F. So all I'm going to do now is write F times E1 plus E1 F star. So it's the most infinitesimal change to the formula. I've done nothing. It's going to, but it's going to change everything. So where do I? Okay. So from this, I can now brutally use this new definition and extend it brutally to not just the Lie algebra, but the entire thing. So definition. So I'm going to define a continuous R bilinear map and I'm going to call circle line. So how do I define it? I can define it on words. And so U, circle line acting on E0 to the N. That's why it's very irritating to have upper indices, you see, because if you want to have N copies, you're forced to put parentheses there. It's just what it does is it sticks the word onto the right-hand side. Oh, this is going to be really irritating. Okay. All right, I'm stuck with it now. So now the inductive definition is that if I have a word that begins E0, I would love to put lower indices. If you allow me to put lower indices. Can I put lower indices now? Because this is going to be a nightmare. So if you don't mind, this is the reason why it's very difficult to keep the notations consistent, because it becomes very ugly.
Low indices, but concatenation.
Concatenation, yeah, the concat. Concatenation, but lower indices for purely notational reasons. Just because I'll have parentheses all over the place, it's going to be a nightmare. So, so it acts on a string of E0s just by gluing on the right. How does it act on this thing? It acts by, every time I see an E1, I put my word on the left of the E1. Then every time I see the same E1, I now put the same word, starred, on the right. And then you keep going. That's a recursive definition of this action. It's very simple. So now let me do an example. Need a nice big blackboard. So I've sort of artificially, by doing this gobbling up this minus sign, I've just artificially extended this action to the entire universal enveloping algebra. So now let's compute an example. And the reason I do this is because it's kind of got an operatic flavor, so I hope it should tie in with previous lectures. So let me compute the action of U on this word. Right? So how do we do it? First of all, we see an E1. So I put U on the left of E1. Okay, and then we see the same E1, so we have to put U star on the right. Then we travel along. E0s don't get anything. Another E1. So we have E1, E0, U, E1, E1, E0. Then this same E1, we get it acts on the right. Then we have the next E1 in which it acts on the left. So it ends up in the same slot. Finally, the next E1 here, you start E0, and we mustn't forget the very final one. Goes on the right. So there should be 6 times here. It's the sum.
There are 7.
1, 2, 3, 4, 5, 6, 7. Ah, that's ominous. Why done that right?
Could be 7.
Yeah, I think it's right. Okay. 7, fine. Yeah, okay. So, comment for the operadists. U circle dot V, of course, is a sum of U circle I V, where circle I means insert the word U before each letter E1 and insert a U star after each E1. And something else at the end. So I leave it to the people to write nice trees. Bruno can do some great trees, and I won't attempt to do them. Okay, so now I want to derive Goncharov's formula from this.
So you are saying that restricted to Lie polynomials, this is the formula I had before?
If I restrict to Lie polynomials, of course, if so U is in Lie, then by this formula it's exactly the same.
It's really nice.
So, oh, thank you. Thank you, Lena.
What's the U at the end?
What's the U at the end? Yeah, so there's this, so this is, yeah, plus,
Oh, okay.
yeah. Yeah, thank you. So I mean, so this thing equals that, and then you add that. It's not part of the equality. Right, so now Goncharov's formula, and then, because I'm going to use this a lot this afternoon. So Goncharov's formula, again, is derived in a completely different way. So in some sense, it's the dual formula. It's not really the dual. The interpretation is actually quite different, but I'll show how to go from one to the next. So what we had before this notation that we had an element uxy that we thought of as the copy of a series in this copy of the groupoid. Okay, so we can do the same thing on the dual. And now let me write, since we're allowed to index each element of the each element of the groupoid by x and y, we can do the same thing with the dual. And so now I'm going to write an element of the dual in a suggestive way. And I'm going to use I'm totally justified in using low notations now. So I'm going to write this for the word EI1, EIN in the copy of O of pi of AB, which is isomorphic, don't forget, to the vector space spanned by words in two letters.
Sorry, why is the seventh term there? The one with a U at the very end?
Because by the initial step in the induction, if I have just an E0, I concatenate on the right.
So when you say you insert a U before AT and a U star after, you also have to add on that last
Yeah,
one.
so that was an answer to someone's comment. I added that here.
Oh, sorry, I missed that. Okay, great.
Yeah, so did I. That's why I added it. So, okay, a word of warning. So when Goncharov does this, he writes this. This is an equivalence class of framed mixed Hodge-Tate structures. But I'm going to derive exactly the same thing by just thinking this as a word in a copy of the Durand fundamental group, and it'll be exactly the same thing. And this is entirely the philosophy of in the style of which I've chosen to present things. So we think of this element as we have from the very beginning. We should think of it as an algebraic version or an abstract iterated integral. So we're thinking of it as the iterated integral from A to B along some prescribed path of some differential form In. In fact, that's how I presented things in the first place. Okay, so there are certain rules which are going to be the analogues of the properties that I did in the very first lecture. So what are the rules? Well, we know that iterated integrals satisfy shuffle products. So this is property 4. I of A WB, so W some word, times IA W2B is I of the linear combination of i's obtained by shuffling together these two words. So this is a linear combination of I, A, something, B, where the something is all the words obtained by shuffling in the middle. Then we have a stupid condition that the iterated integral from 0 to 0 is a completely trivial iterated integral, so this is 0. Then we have that the iterated integral from 1 to 1 along the trivial path is also 0. And then we also had reversal of paths, which was second property, I believe. Equals, and the reversal of paths did what? It reversed all the differential forms and gave a sign. So that's exactly the star. And of course, so in this notation, A and B are 0 or 1. Okay. So via these relations, we can always bring back any element I, A, B, for A, B arbitrary. We can always, by using these relations, bring it back to an element I naught something W prime in the copy between 0 and 1. Because if A and B are both naught, well, it's 0 anyway. If they're both 1, that's 0 anyway. And if it's 1 naught, we can flip reverse paths and go to 0, 1. So we can always bring ourselves back to this copy. So first let me quickly show the infinitesimal coaction. So for that, I look at this thing modulo products. So the indecomposables of this is equal to O pi 1 divided by products. So the standard thing for quotienting by products. And now I'm going to define the infinitesimal coaction. So definition. So this is what I call the infinitesimal coaction. O pi 1 maps to indecomposable elements in O pi 1 tensor Q O pi 1. So now the map takes one of these symbols, A naught, of course A naught is naught, and A n plus 1 is 1, but the formula is good to write it more generally. And it maps to the sum, P equals naught to Q. P is naught, no that's rubbish, P is naught naught less than equal to P. Let's do that. Of I. So here you take the consecutive sequences of length Q. So this is a consecutive, so I have a bunch of words. This is 0, 1, these are words. I take just the consecutive sequence, consecutive subsequence, and then tensor it on the right-hand side with everything that remains. So you go up to P, and you skip what you've removed. You skip the chunk that you've cut out, and then you go all the way up to the end. And of course, so we've seen that before as well.
You don't need Q greater P, do you?
I beg your pardon?
Don't you have that already included? That Q is AP. If you have P plus.
Oh yeah, sorry. Yeah, P. Thank you. P comma Q. Maybe that's.
Yeah.
Yeah.
But Ethan, why do you need to take I on the left?
Thank you. I need a class.
Why?
Because I'm viewing elements in here, I'm viewing them as symbols as it's words.
I understand. Why do you need to take only one interval instead of what Goncharov does, which is take whole polygons?
That's exactly the whole. I'm going to come to that in a minute. So that's an extraordinarily inefficient way of computing this.
Yes. Well, I agree. But now that you have the other formula for the general case.
Yeah, but there's a very different reason. So it's very bad to work in a dual because if I want to do the Ihara action, I have to multiply all possible series. I have to take the generating series for all multiple zeta values and compute the entire thing. So if I'm in weight 15, it's 2 to the 13. It's an enormous calculation. The point about this is if I want to look at a single element, I can decompose it. So it's an infinite gain in efficiency.
So here you're
psychologically
utilizing the formula you gave, Li times R.
Absolutely. And then I'll
But
exponentiate
you
it in a
can't do
minute.
the general case.
I'm going to do that in a second, and I'll finish with that. Yeah?
I can't read it. But is it the case what you're doing is taking out the segment from P to P plus Q and put, thank you.
So I was going to do that earlier, but I was.
It's doubling AP and AP.
Yeah, exactly. So AP, which is the boundary here.
Yeah. It's a couple and product.
So here, strictly speaking, I'm being a little bit sloppy. E0 is going to be 0, E1 is going to be 1. I'm going to pass between these notations continuously. Because when I wrote the definition, boundaries are zeros or ones, they're not letters, but we do this. It's the same thing.
Don't you have a certain constraint on Q because you want to live in the so your left-hand term should live in the indecomposable, no? So Q should be greater than 1 or 2.
Yeah, but so actually, I should say the empty iterated integral is 1. Remember that the constant integral, so where there's nothing in between, I don't know how to write it, is always the constant one. This was the thing it's the constant iterated integral. So I can put a condition on being strictly bigger than 0. That's the same thing.
Why don't you have a product of two intervals on the right?
No, never. On the right?
On the right.
No. Yeah, I'll draw a picture in a minute. Should I draw a picture now? Yeah, I'll draw a picture now. Okay, so what this map is. So one way to visualize it, which is due to Goncharov, well not this, but the next thing that's going to come later. A7. So what is the formula? The formula says choose any segment. This one. And in this linearized action, you get the subsequence 2, 3, 4. So I take A, 2, 3, 4, and tensor with everything that's left. So if I, A0.
You shouldn't do tensor with the product of the pieces that are left?
Sorry? No. This is
When
great.
he defines it, he tensors with the product of the pieces that are left, so the shuffle product.
I'll come to this formula in a minute. Maybe that'll answer it. I'll derive this formula in a minute.
No.
No, a main piece? No.
So that's a typical term in the formula.
One on the left.
And I want to call this map D.
First one.
The main.
So this is the map D.
Cut off, then it's-
Right. So the claim, which I'm not going to completely prove, that this is exactly dual.
Oh, the product's on the other side.
This is exactly, Goncharov formula is back the wrong way around, so it's the other way around. So this is dual to the linearized Ihara action. So let's have a look with some colored pens. I'm really running out of time. Let's look at what happened in this formula. So what's going on? We had this, this, and this. So this formula is obtained by inserting words into a word. The dual is pulling words out of a word.
If I can make an operative comment.
Oh, please do.
We have these pictures for A infinity algebra. The definition of A infinity algebra is
In the bar construction, absolutely,
yes.
yeah. I completely agree. But you have the boundary conditions are slightly If you have a two-sided bar construction, maybe it's a two-sided bar construction.
Either you take the bar construction, not the simple one, you take a co-derivation with respect to 0.
Yeah.
So it means that you compose the first string of thing and then the rest. And if you dualize that,
Yes.
you have certain string and you extract.
I agree, but we have to be a little bit careful about the repeated
Maybe yes.
repeated conditions.
Okay, yeah.
So that's the only thing. But I agree in philosophically. I agree.
The correct comment came from behind. It's the cup 1 product. That's exactly what it is.
So it's related.
Yeah.
And
That's why I agree.
The cooperative structure.
Yeah, that's why I erased it. Sorry. So I erased it. Okay, proof. So can I just do this quickly? The proof. So what happens? We take E naught. Well, every time we see an E naught E1 in this sequence, every sequence E naught E1 becomes E naught U E1. Okay. Every time we see a sequence E naught E naught, well, nothing happens because we don't ever see the E naught. So that goes to 0. So that's precisely this condition that I naught W naught is naught. Then every time we see a sequence E1 E naught, it becomes E1 U star E naught. And every time we see E1 E1, it becomes the U gets inserted on the left, but then it also on the right of the first E1 with a star, but then it also gets inserted on the left of the second one. And because we're in the Lie algebra, U equals minus U star. So they cancel and we get 0. And these formulae, so something beginning in naught and ending in 1 stays the same. Something beginning and ending in naught goes to 0, likewise with 1. And something beginning with 1 ending in naught gets a star, is on the nose these formulae I've written here. So it's an exercise to check that this formula is dual to that one. And so so let's have a look on the example. These things add up to 0. And the way to think of it is to put a little E naught at the beginning, because we're working in pi naught 1, so we have to put E1. And this formula then is precisely the dual of this operator P on the note. Okay, so I'm sorry for taking so much time over this, but it's not written anywhere in the literature, so I thought it would be good to do it properly. So the details of an exercise. And finally, to get Gontcharov's actual formula, I just exponentiate. Sorry, I'm really running over time. Really finish up now. I'll just write down the formula. I'm not going to use it. So you just exponentiate this formula, so we get delta O by 1 goes to O. So you exponentiate on the left. And now the map is the sum over all possible so equals naught equals n. Then I take the product of over all subsegments AIP plus 1, AIP plus 1, tensor all the nodes. So it's better to illustrate this on a diagram. So the analog of that diagram is this diagram. So obviously when you exponentiate, you instead of pulling out one sequence, or inserting a sequence, you insert it many times, or pull it out many times. And the multiplication is, of course, shuffle. So now you do a complete dissection, something like this, and so Gontcharov's coproduct of the one he wrote down is this thing times the next segment A4, A5, A6. I've been a bit over enthusiastic with the segments. Tensor cancel with all the nodes. So here are the nodes. So I'll write it in blue. A0, A1, A2, A4, A6, A7. So there, I've derived Concho's product from the Ihara bracket. So I should say this is Concho, except that he wrote the right-hand factors the other way around. So but I should just, as a final comment, I should say that these formulae contain exactly the same information. But it's extraordinarily inefficient to calculate this because if you have a polygon with 50 segments, this is quadratic in the size, whereas this thing will require more computing power than the entire planet or something very quickly. So
And just because the product on the left is a shuffle product, right?
the left is a shuffle product, yeah.
This D is derivation.
D
is derivation.
yeah, I call D for derivation. So it's the infinitesimal version of this.
This one.
Yeah, it's acts by.
This is dual derivation.
Yes, it's a co-derivation.
This is a co-derivation? No, I don't understand.
This thing is should be a co. Yeah, so this thing is a co-product. It's a homomorphism for the shuffle product. Therefore, this thing is a co-derivation.
Thank you very much.
Concrete calculations.